Good afternoon. I am Andrew White, Director of Valve Products with the Lesman Instrument Company. Thank you for taking the time to attend our webinar this afternoon. Our topic today is Myths and Realities, Why Control Valve Sizing Matters. This webinar will be recorded and posted to our website for anyone to listen to at a later date. Please enter your questions in the question section of the menu bar. We'll answer those at the end of the session. I'm pleased to announce the speaker for today's presentation, Jack Harold. Jack started working for Zurich in 1984 as an application engineer. Throughout his career, he has been involved in control valve sizing. In 1987, he developed one of the first PC-based sizing programs, Alpha 1, which is still used extensively today. He served on ISA's S75 committee, which developed the flow equations for control valve sizing and testing. He is currently the training manager for Zurich. Jack, you may begin your presentation.
Thank you, Andrew, for the intro, and I'd like to thank Lesman for hosting the webinar and inviting Zurich to participate. And then I'd like to thank the attendees for giving us your time to attend the webinar. Let's get started. So valve sizing, what can go wrong? The most common scenario is the valve is oversized. With an oversized valve, you're potentially paying a much higher cost. It is not unusual for larger valves to be 1 or 2 sizes less than the adjacent pipeline. This could reduce the cost of the valve 20 or 40% compared to a line size valve. Increased maintenance. If a valve is oversized, the interior trim of the valve, whether it be a plug, ball, disc, will be located closer to the seat. When the fluid goes through that valve, it goes through the smaller reduction between the plug, ball, or disc and the seat. It can create jet velocities inside that body. Most control valve bodies are cast, and if they're impinged by jets in one isolated area, it's very common to see those valves eat it out from the inside out, which could cause weeping externally to the body. Poor performance. We'll talk about this in more detail in a future slide, but an important concept is a control valve has an infinite number of positions it can achieve between 0 and 100% open. If you size the valve too large and it's operating at 25% open compared to 75% open, you could really diminish the amount of control steps you can take, which could lead to poor process performance. The other scenario is undersized valve. That's probably the least common. Undersized valves will limit plant capacity. Now I have 2 animations here of oversized and undersized valves. And obviously they're animations. You would never want to use a valve larger than the line size for a control valve. And valves should not be smaller than 1/2 of the inlet pipe size. So let's take a look at what we're going to talk about today. We're going to define what a control valve is, at least for this presentation purposes. We're going to discuss control valve performance and what makes a good control valve. We're going to talk about the control valve function, what it does in a process control loops and how it interacts with the other instruments. We're going to take a look at control valve sizing, what it is. And we're going to take a look at sizing data, where it comes from. And to do that, we're going to develop a system curve for a process with a centrifugal pump. And then we'll take a look at what changes in the system if you replace that fixed drive centrifugal pump with a VFD, our variable frequency drive. So what is a control valve? It's a pretty open-ended question, and there's many correct answers. So there's many style of valves that can be used for control. We go from knife gates to butterflies to globes to plugs to different types of ball valves. When I talk about a control valve for this presentation, I'm going to be talking about a valve, an actuator, and a positioner combination. A valve is the device that creates a restriction to flow. All it can do is increase the amount of flow it allows through the pipeline or decrease the amount of flow. The actuator is the device that provides force to move the valve open or close. And the positioner is the instrument that connects to the control system, which will tell the valve either stay in the same position or to increase the flow to the system or to decrease the flow to the system. So what makes a control valve good, or what are some of the criteria of a good control valve? Well, the first one you talk about will be repeatable, accurate movements. There's been a number of tests, a number of outside entities that have tested control valves and have come up with a standard that says a good control valve will have about 200 positions, repeatable positions between completely closed to completely opened. That's about 0.05% repeatable accuracy. So if you take a look at what that means, if you had a system with a maximum flow rate of 1,500 gallons per minute, and that valve was sized for 25% open, it was oversized, you would only be able to use 25% of those 200 positions or have 50 usable positions of that valve. So what that means is every time that valve would move, you would get a 30 gallon per minute minimum flow change. Conversely, if you have that same system with 1,500 gallons per minute maximum flow, and you would size that control valve for 75% open, you'd have 150 positions. That would give you 10 gallon per minute flow change every time you move that valve. So from a loop tuning standpoint, you're going to have a much more stable loop if you can make smaller incremental positions. And from a process control standpoint, it'll be much easier to maintain your process control standards by making smaller changes with the control valve. Analogy I like to use is cruise control on a car. If you would set your cruise control at a certain miles per hour, every time you hit the advance or the decrease button, it moves up or down 1 mile per hour. Well, if that button would move the valve or move the speed of the car up or down 5 miles per hour, it would not be acceptable performance. We've done a lot of studies of control valves in loops, and we found that the movement of the valve, or the smallest attainable movement, is a major contributor to loop instability. Tight connections are very important to a control valve, and that includes the valve to the actuator and the actuator to positioner. You want connections that are clamped or solid. You do not want connections that allow any type of slop or hysteresis. Proper assembly is very important and often overlooked. There are typically brackets that will mount the valve to the actuator and mount the positioner to the actuator. You should always tighten the connections between the valve and the actuator before you tighten the bracket that connects the two. And the same would be for the positioner to the actuator. Make sure that connection is tight and adjusted before you attach or tighten the bracket that holds the positioner to the actuator. The reason for doing this is that allows the actuator to center on the valve shaft and the positioner to center on the actuator drive shaft, so you don't have side loading or create unnecessary friction. Friction is probably the biggest deterrent to control valve performance. When you have a good control valve, it's going to have large bearings for both the valve and the actuator that allow ease of movement. Actuator seals are important. The image we have on the screen now shows a diaphragm actuator, which has a rubber diaphragm that's very low friction, and that is one of the reasons it's used extensively on linear and rotary blow valves. Cylinder actuators can also be a very good actuator for control, but you'd want to stay away from, in most cases, elastomer seals, as the elastomer will have a much higher rate of friction than, say, a Teflon or some type of polymer seal. And then a quality positioner. You need a positioner that can deliver small incremental air packets to that actuator to allow it to move very small incremental steps so you can achieve that control valve performance. So when you take a look at what a control valve does, here's the schematic of a feedback control loop. In this schematic, you have a process. That process could be measuring flow, pressure, temperature, level would be the four most common. You have a sensor and transmitter, which reads the flow, pressure, temperature, level of the process, and that sends a signal to the controller. That controller has a set point. That set point could be set by human interface, or that set point could be set by another process or another piece of equipment in the system. And that is where the system wants to run. And so the controller could be a distributed control system, a DCS, or a PLC. It will compare the output or the input from the sensor transmitter to the set point. And if that is in line, if they equal, it will tell that final control valve element to stay in the same place. If it's off, high or low, it'll tell the control valve to open or close to adjust and get the process back into the set point. This is a recurring process. This is constantly going. Anytime there's upsets to the process, the sensor transmitters providing that information to the controller and it's adjusting the valve. It's worth noting that all the valve can do is increase or decrease flow. So if you have a valve that's controlling pressure, temperature, level, that type of control valve is based on what the sensor transmitter is reading. So what is valve sizing? Valve sizing is the determination of two CV values. There's a system CV, a CV that is required by the system. This CV is mathematically derived based on equations published in ISA, Instrument Society of America, standard 75.01. You have a valve CV. This is the CV or capacity that a valve can provide. This CV is determined by test, or in large valves, simulation. Test procedures are defined in ISA 7502. Valve sizing in its simplest form is selecting a valve with a tested CV that is greater than the system CV. Now the takeaway here is you do not want a valve CV that is 1% or just barely over the system CV. Now the amount of safety factor or value tested CV over system CV, that will vary based on valve style and process conditions. But in its simplest form, if the tested CV of the valve is greater than the required CV of the system, that is what you're trying to accomplish when sizing a valve. So we talked that equations to determine the valve flow coefficient for the system are defined by ISA 75.01. And to perform the calculations inside that standard, you need all this system process data. You need to know the flow rate, you need to know the pressures, inlet and outlet, and you need to know the fluid properties, which are typically going to be based on temperature. The point I'm trying to drive here is that process of that system has to be almost completely designed before you even look at sizing a control valve. The second CV is the valve flow coefficient. This CV is determined by test or, in larger valve sizes, simulation. CV is defined as the number of gallons of water at 60 degrees Fahrenheit that will flow through a valve with a 1 psi pressure drop in 1 minute. The test procedure is defined by ISA 7502. And if you look on the bottom left half of the screen, you'll see the schematic for testing the CV of the valve. You will have a thermometer to measure the temperature of the fluid. You will have a flow meter. And in that line, you will have the test valve. Ahead of the test valve, you will have a pressure gauge. And downstream of the test valve, about 10 pipe diameters, you will have another pressure gauge. Behind the test valve, you will have a flow control valve. And you will adjust that flow control valve to test the amount of fluid that is passing through that test valve with the 1 psi pressure drop. And if you do that at 100% open, then you could take that value and you would plot it on a graph. And I have a flow characteristic graph in the middle bottom of the screen. So you test the valve at 100% open, determine the gallons per minute of that 60-degree water with the 1 psi pressure drop. You would do that at 80%, 60%, 40%, 20%, and you would develop what's called the flow characteristic. And the flow characteristic is the relationship between the CV, or in this case, percent of maximum flow, versus the valve percentage open. So where does data to size a valve come from? So we're going to take a look at a system curve. So system curve shows the relationship between flow rate and pressure. It provides the maximum system flow rate, and it defines the valve pressure drop. So here's our simple system. We have a tank A on the bottom left-hand part of the screen, and we need to transfer fluid to tank B on the right-hand part of the screen that's at a higher elevation. We decided we're going to use a centrifugal pump to transfer this fluid. We know, based on the requirements for the draw out of plant B, what the flow rate will be for all conditions. We know what the fluid is and the temperature of the fluid, and that will give us the fluid properties such as vapor pressure, specific gravity, critical pressure. And we also, the pipe size is also selected before the valve sizing is even considered. And the pipe size is selected based on the recommended pipeline velocities for the type of fluid, whether it be clean or dirty, that is in the system. So as we start to develop that system curve, and again, that is the relation of pressure to flow rate, the first thing we need to look at is static pressure. Static pressure is the amount of pressure that pump must generate before any flow will occur in that pipeline. And it's the elevation head between the level of tank B and the center line of the pump. The static pressure does not change based on flow rate. It is constant for all flow rates. The next part of the system curve is dynamic pressure. Dynamic pressure is your pressure loss due to flow. Dynamic pressure does increase as the flow rate increases. It's basically a quadratic relationship. So if you double the flow rate, you will quadruple the dynamic pressure. So once you've developed the system curve to this level, where you have the pressure versus flow, and you have the static losses or static pressure, and dynamic losses or dynamic pressure, you need to select your pressure source. And to do that, we would look at a pump curve. So a pump curve, there are three typical selection factors. The impeller size, the larger the size will deliver, of the impeller will deliver more pressure, more flow. And then there's also efficiency rating and energy usage. So you could have a whole class on pump selection and the criteria for that. It's almost like valve sizing. But an experienced engineer will select a pump based on the dynamic losses and the static losses and use that pump to develop the system curve. So this is what your system curve would look like without the control valve. You have your static pressure, you have your dynamic pressure, and you have your pump curve. And if you would start that system up with no control valve in line, the maximum amount of flow that system would generate would be when the pump curve intersects the dynamic pressure curve. So that's the maximum system flow rate without a control valve. So we're going to take that system curve now, and we're going to start looking at how that defines valve pressure drop. The important takeaway here is the system always operates on the pump curve. So the combination of the static pressure, dynamic pressure, and the valve pressure drop must equal the pump outlet pressure at the desired flow rate. Important point, so let me state that another way. To achieve the desired flow rate, the control valve needs to provide the required pressure drop so the system losses intersect the pump curve at that point. So a system always operates on a pump curve. Major point to determine the valve pressure drop. A static pressure plus dynamic pressure plus valve pressure drop has to equal the pump pressure at the desired flow rate. Valve pressure drop is independent on where the valve is installed in the system. That valve could be installed close to the pump, it could be installed close to tank B, or somewhere in the middle. the pressure drop of that valve does not change based on installation in the pipeline. For centrifugal pump, as flow rate increases, the control valve pressure drop decreases. When data is sent to me for sizing a control valve, one check I make is to verify that the pressure drop at max flow is less than the pressure drop at min or normal flow. This is based on dynamic losses. Losses due to friction increase as the flow rate increases. The pressure drop at max flow has to be less than the pressure drop at minimum or normal. Potentially could be very close, could almost be equal, but it cannot be more. If it's more, then you're not being given valid data for sizing a control valve. This is your final system curve. So the new line added shows what that max flow rate would be for the system with the control valve at 100% open. So it's at 100% open, it is basically another fitting or fixture inside that piping system. And the flow rate, if you would turn that pump on with the valve at 100% open, would provide less flow rate than the valve, than if the valve was not installed in the system. So the system curve helps us define, or does define, the pressure drop for the valve. Common question I've had is, what is the pressure drop of your control valve? And the correct question, that's not a valid question. Pressure drop of a control valve is defined by the system. The control valve has to create the pressure drop the system wants for the desired flow rate. So now we have pressure drop. Another critical factor we need for sizing the control valve is the valve inlet pressure. So if we take a look at our system, on the left with the tanks A and B and the centrifugal pump, and we have the system curve on the right, which defines the pressure drop. We need to know the inlet pressure to size that valve. So one option would be to put the valve close to the pump. And in this location, the inlet pressure to the valve is effectively equal to the outlet pressure of the pump. Might be a little bit of loss there for some piping and friction and elevation, but for practical purposes, the inlet pressure to the valve would be the outlet pressure of the pump. If we would move the valve to location 2, the inlet pressure to the valve would be equal to the outlet pressure of the pump minus any friction losses that occur before the valve. So it'd be somewhat less than location 1, but not significantly less, depending on the friction losses. If we would move the valve to location 3, which would be located next to the tank, the inlet pressure to the valve would be the lowest value. It would be the outlet pressure of the pump minus the static head due to the change in elevation between the pump and the level in the tank, minus any of the dynamic losses, which are the losses caused by friction as the fluid flows through the pipeline. So which location is better? 1, 2, or 3? To determine that, we need to take a look at pressure drop ratio. So pressure drop ratio equals valve pressure drop divided by valve inlet pressure. So in location 1, closest to the pump, since the pressure drop is independent of location, the pressure drop is always constant, no matter where the valve's installed in the system. Now the inlet pressure is dependent on location. And at location 1, because the inlet pressure would be the highest, it would basically be the pump outlet pressure. Location 1 would have the lowest pressure drop ratio. Location 3, where the valve is located very close to tank B, the discharge, that would have the highest pressure drop ratio. Low pressure drop ratio is better. Closer to the pump or any pressure source is usually better for noise, cavitation, and vibration. And in this scenario, or in almost every system I've seen, closest to your pressure source is going to give you the lowest pressure drop ratio. Okay, when the system curve is completed and the physical location of the valve is determined in the system, you now have all the information required to determine the system CV. And on the right-hand side, we have a screenshot of the Alpha 1 sizing program. All manufacturers that I'm aware of that offer control valves will have their sizing software. The Alpha 1 software is available from Desoric's website, desoric.com. And it will allow you to input the data from your system into size the valve. A couple things to note with sizing programs. Because the control valve is sized after the piping system has been designed, it is very common for the valve size to be less than pipe size. The ISA equations take into account the pipe reducer that reduces the inlet pipe to the smaller body size, and the pipe expander, which increases from the valve outlet to the larger pipe size. That is taken into effect with the ISA equations. It looks at the valve and the fittings as one unit. For gas systems, it is common for outlet piping to be larger than inlet piping. Gases are compressible, and as the fluid or the gas flows through the valve, there will be a drop in pressure. At the lower pressure, the volume of the gas will expand, and a larger pipe will keep that velocity within the design limits of the system. Okay. I'm typically provided sizing data via two sources. For new plants, the ISA S20.50 data sheet provides all the information required by ISA 7501 to calculate the system CV. It also provides requirements for the valve, actuator, and accessories. The second source is from the control room. For existing valves, this is the best source for sizing information. So many times I've been sent ISA S20.50 sizing sheets that are several years or decades old to size an existing valve. In most cases, the process has changed considerably. Control room data should be used to verify the sizing data. Like most things, garbage in, garbage out. You need accurate data to properly size a control valve. Let's do a little recap. Control valve performance. The valve, actuator, and positioner assembly are all equally important in the valve achieving a good incremental control of 200 positions for its full stroke. I like to typically size valves 60 to 80% open at max flow. That allows you to get good incremental control as you're using a large sweep or a lot of the positions that the valve can achieve. Control valve sizing. There are two CV values defined by ISA. The system CV is derived mathematically by ISA 7501. The valve CV is tested, or large valve simulated, by ISA 75.02. In a nutshell, valve CV has to be greater than the system CV, but if you look at the 60 to 80% open at max flow, that gives you some indication of the type of safety factor you would want based on variables in the tested CV of the valve or in the system data used in the equations. And control room data is just a good source to validate existing controls. If I'm given an old ISA S20.50 data sheet for a valve that's failed, and they want me to size a new valve because the old valve has failed, I'm guessing the failure of the valve, whether it be performance or mechanical, is based on valve sizing data. So I always encourage to get data from the control room when you're sizing for an existing valve. From a system curve standpoint, that is the relationship of flow rate versus pressure drop. There are three components to the system curve. There's the pressure source, the dynamic pressure, and the static pressure. The system curve will define the valve pressure drop. It does not define the valve inlet pressure. The pressure drop is constant no matter where the valve is installed in the system. The inlet pressure is very dependent on where the valve is installed in the piping system. Inlet pressure determined by location. And the big takeaway is the system operates on the pump curve. So the control valve must provide enough resistance to that system so the losses from the piping and the control valve combined will intersect the pump curve at the desired flow rate. So let's take a quick look at fixed drive pumps versus VFDs, or variable frequency drive pumps. So as we talked about, in a fixed pump system, the system always operates on the pump curve. To achieve the required flow rate, the combination of the static pressure, dynamic pressure, and control valve pressure drop must intersect the pump curve at the desired flow rate. And as you can see from the graph, if you have a pump that is generating a lot of pressure at a given flow rate, that control valve will have to drop a lot of that pressure to get the desired flow rate. That is overconsumption or waste of energy. So that's where VFDs come into play, or that's the major benefit of the VFD. The VFD without a control valve, the system operates on the system loss curve. So one way I like to look at it is if you had changed the impeller in a pump, you'd get a different pump curve. While by using variable frequency drive, you lower that pump curve at the output of the pump, decreasing the energy consumption until the pump curve intersects with the dynamic pressure curve. So big difference between the fixed drive system on the left and the variable drive system on the right. One of them operates on the pump curve, the fixed drive system, where the VFD system operates on the dynamic pressure or the dynamic loss curve. So some frequently asked questions. If we install a control valve that has a larger CV, will that save us energy? Probably drive this point home, maybe more than necessary, but the system always operates on the pump curve. What that means is to provide the specific flow rate the system requires, the combination of the static loss, dynamic loss, and pressure drop from the control valve must equal the pump outlet pressure at the required flow rate. If a larger control valve is installed, the valve will need to close further to provide the required pressure drop. Operating a valve closer to its seat can increase required maintenance. Talking about those jets forming in the body typically being cast and susceptible to any isolated type jets or erosion, and will deliver poor performance. You will use less of the 200 positions a typical control valve provides and will not be able to achieve good control, and will potentially have loop tuning issues. Pressure drop is determined by the system. The valve moves to provide the required pressure drop. Putting in a larger valve will not change the pressure drop of the system. Will valve maintenance be reduced if we move the valve further away from the pump where it has a lower inlet pressure? Inlet pressure is determined by location of the valve in the system. It does not affect valve maintenance. Installing the valve closer to the pressure source is better. That provides a lower pressure drop ratio, which can reduce noise, vibration, and prevent cavitation. Proper installation in the pipeline is important. Control valves should be installed a minimum of 6 to 8 pipe diameters away from pumps, elbows, or other similar items that can skew the flow. And when you're dealing with rotary valves, especially larger size valves, the proper installation is to install those valves with the shaft in the horizontal position. This does two things. One, it gives better bearing support for the ball plug or disc that's inside the valve body. Again, the larger the valve, the more important that is. And second, if you have a segmented ball or a plug valve, you can now rotate the plug or the ball up to the top of the valve body. What you're trying to do here is, if there's, especially for dirty surfaces where there's any fallout of media in the bottom of the pipeline, we want to keep that away from the bearing area of the valve, or we want to keep that away from the movement of the valve, and then always have the plug or ball rotate to the top of the pipeline. With a fixed drive pump, if we replace all of our isolation valves with 100% area valves and install low head loss fittings, how much energy will we save? So as we talked, in a system with a fixed drive pump and a control valve, installing 100% area valves and low head loss fittings will not save energy unless changes are made to the pump. In fact, reducing the dynamic pressure losses will only increase the amount of pressure drop that the control valve needs to provide. This could lead to cavitation and higher noise levels. So if you would install 100% area isolation valves, which have more head loss, and other low head loss fittings like sweep elbows or low head loss check valves, what you're doing to that system is this dynamic pressure curve would actually be less. Well, if you need to operate on that pump curve, you've just increased the amount of pressure drop that valve needs to absorb to get the desired flow rate. Conversely, with the VFD pump, if we replace all of our isolation valves with 100% area valves and low head loss fittings, how much energy will we save? In a system with a variable frequency drive and no control valves, installing 100% area isolation valves and low head loss fittings will save energy. So if your dynamic pressure curve has a lower profile due to the low head loss fittings and 100% area isolation valves, the VFD pump will be able to operate at a lower energy consumption and provide energy savings. So again, big takeaway is pump system operates on the pump curve with a fixed pump drive, and with a variable frequency drive, the system operates on the dynamic pressure curve. Oh, I messed that up. Sorry, Andrew.
That's no problem.
Open for questions.
Yeah, we've got a couple of questions coming in already from the field. So first question was, why are oversized valves more common than undersized valves?
From what I've seen, it has to do with conservative engineering. And so when they design the system, they will estimate the friction losses to be higher than what they are, or when they select a pump, they will estimate the pump to give out a lower pressure at a specific flow rate. And both those factors mean the valve has to take more pressure drop. And if the valve takes more pressure drop, it's going to operate at a position closer to the seat and thus be oversized, which increases maintenance and decreases performance.
Yeah, that makes sense with what I've seen in the field too. So next question we've got here is, are there certain styles of valves that are better for control than others?
So that's a broad question. I think the way I'd answer that is it depends on, there's a couple factors in play there. Probably the most important factor is the media. If you have a media that is dirty or has a lot of erosives in it, sand, grit, abrasives, you would want to use a control valve that would have a clean flow path. And what do I mean by clean flow path? You would not want to use a butterfly valve where the disc in the shaft is right in the middle of the pipelines exposed to that abrasive process media. You'd want to use a plug valve or a segment of ball valve or segment of plug valve that has a two-piece shaft. And so the body has a clean flow path, and the high velocity will occur between the plug baller in the plug or the ball in the seat. By doing that, you can eliminate some of the erosion that would occur in the body. So if you have a dirty service, you want to be very cautious or conscious of the flow path through the valve. You do not want to let that fluid impinge inside the body. You do not want to create more turbulence in the body from the flow than necessary. The other factor would be friction. I'd look at styles of valves that have lower friction. So lower friction would mean larger shafts. I'd also look at styles of valves So on the elastomer seated butterfly valve, if the disc is in constant contact with the seat all the time, rubber has very high friction, and that friction moving the valve intermediate positions might be very hard to attain versus a high performance butterfly valve, which uses Teflon. So I guess a broad answer to that is whatever style of valve will provide the minimum amount of friction is going to give better control. And if you have dirty surfaces, be very conscious of what's inside the middle of that valve as the fluid is flowing through it.
Okay.
Long answer.
No, that's a good answer. Appreciate that. Looks like that's it. Any last minute questions coming in before we wrap up here? Okay, I think that'll be it. So Jack, appreciate your time today. And to all our attendees, thank you for joining us this afternoon. This concludes our webinar.
All right, thank you.